Hey everyone, and hope Codejam's going well for everyone. I thought this weightlifting problem looked super interesting, so let's have a go at some live coding. And I have cheated a little bit. I've had a little bit of a look through the editorial, the analysis. So let's try to make sense of it, and I'll try um, write down a few steps and talk you through what I'm thinking about and how I'm solving it. But I'll mostly be focused on the coding. I'll provide a link to the problem, and I'll provide a link to my code afterwards. So check in the description for that. Um, but yeah, essentially, we're at the gym, and we've got 100 exercises here to do in order, and each exercise needs a different configuration of weights. So we might have to add some weights. We might have to remove some weights between exercises, and we have to minimize the number of operations. So adding a weight costs one, and removing a weight costs one as an operation. And since it's a stack, if you have to remove a weight from near the bottom of the stack, then you have to remove all of the weights above that. So that's really bad. So one strategy could be to look at which weights you need to use a lot in the upcoming exercises and try to have those towards the bottom so you don't have to and store weights that aren't used very often near the top. Um, but yeah, let's have a bit of a deeper look at that. So if I've just got one exercise, let's just say it's got three weights, then I have to add these three weights on, and then I have to remove the three weights. So the answer is going to be 6. So 2 times 3. Whereas if I have two exercises, then and this is where I looked at the analysis. So it's a pretty cool insight. Um, you have to combine a few insights, but if you look at what they have in common, then obviously you want to put those on the bottom. And so when we go between exercises, these can just stay on the bottom, and so that saves us some operations. So the answer will be twice. Like all of these, we have to add them once, and then we remove them here. So it'll be 2 times however high this is. Um, and then we also have to add and remove this, so it'll be 2 times that. And then we have to add and remove these ones. And yeah, we have to of this. So it's basically 2 times this plus 2 times this plus 2 times this. So that seems pretty straightforward. What if we have a third exercise now? If it had the exact same ones in common, that's great. But yeah, it's unlikely. Um, we can kind of follow the same way of thinking. It's like, what do they all have in common? Let's put those at the bottom. So then it's just twice that, adding and removing at the end. But now it's not really clear what to do next. Like, do we want to look at, like, if we wanted to solve for what's remaining out of these two stacks, then we could again do what we did before and look at what they have in common. But then that's kind of leaving this guy out because they might have had something in common as well. But the thing is, if this guy had something in common as well, then we would have made this bigger, right? So we know if these two have something in common, we know that this guy doesn't have anything in common. And also, if these two have something in common, then this one doesn't have anything extra in common with what's in common between these two, because otherwise this line would be higher. And so what that means is we can try splitting like a divide and conquer solution where we look at this and this separately, like the two halves separately. We might look at this and then look at this. And potentially we could even look at all three separately. But that would be the same as doing like this and then like splitting that recursively and splitting that. And it would also be the same as like splitting this way and then recursively splitting that. So basically we can just do the divide and conquer. So the trick is for some interval from left to right, left to right. We'll look at what's in common, and then we'll try all possible split points and see which one's best. We don't actually know where to split, so x plus 1 will be our split points. So this is like the x. The x will just be an exercise between L and R inclusive. So this is a little bit better. So then we can recurse on these two subproblems. So our recursion will solve for that and solve for that. So the answer will be that plus that. So twice that height of what they have in common. So we need to be able to work out how many weights there are in common between an interval of exercises between L and R. And then recursively, we can solve this area. So that would just be looking at it as if we only had exercises from L to X, but actually we've already counted this, so we actually don't want this bit here. So that's what we'll need to subtract this and this away from it. And that will give us this bit here. So then we'll get this bit and this bit by just having this bit subtracted with this bit and this bit subtracted with this bit. And in a similar way, we'll grab this and this. And we'll just keep going until we get the solution. Cool. So I should probably mention how to get the weights in common and how we're going to represent this problem. So use a matrix of E0, E1, E2, dot, dot, dot. And for each exercise, we have a count of how many weights there are of each type. E0, E1, E2. And so this might be like F3, 5, 6, 2, 1, 11, 5, 12, 0. Let's just say 3. Maybe I'll put some rectangles around to make it a bit more clear. These are our 8 stacks of, these are our weights for each exercise. And if we want to know what's in common between E0 and E1, we can just do one above them. So that would be the minimum of 3 and 1. So we just have one of type 0 in common between E0 and E1. And we'd have 6 of the next step. And we have 2 of the next step. Oops. Let me drop. Yeah, so let's drag this down a sec. And then we can do something similar to find out what's in common between E1 and E2, and then we can do something similar to find out what's in common between these two, and this will be what's in common between E0, E1, and E2. So you can kind of build up this pyramid. I guess it's kind of similar to how Pascal's triangle works. And so we can kind of each time just recalculate. So for each test case, we'll scan these in, and then we'll just rebuild these above. And so this will just be a matrix of multisets, I guess. So we'll just have I and J like that. And we don't actually need to know for this part over here. We don't actually need to know what's in these multisets. We just need to know how many weights there are in common. So we can make a matrix called size, which will be how many there are in common. So if we add this up, 6 plus 2 plus 3 is 11. 11 plus 1 plus 5 is 17. 3 plus 0 plus 12 is 15. 2 plus 6 plus 1 is 9, and so on. So we'll have this kind of triangle matrix of, so for each pair from L to R, we'll know how many weights they have in common, which is cool. So yeah, let's start coding this up. So this arrow. Cool. So I'll just call this size L equals how many weights are in common between and that. Inclusive. For the recursion, which will be this bit, we'll have M L equals, and what will that be? So we use this size LR to get the size of this, and then we need MLR to get this bit and this bit. So extra ups. Yes. Yeah, read the analysis if you want a better explanation of what this is. Okay, so let's get the problem input. So for each of the 3 test cases, we get given how many exercises there are, how many weights